When riding in your hot air balloon, the hot air balloon is rising steadily at a speed of 2.98 meters per second. Let's say you drop a cell phone. We want to describe V frame, V, and V prime. All right, so I would say that the best choice here would be that V frame is the moving hot air balloon. All right, velocity of the hot air balloon's reference frame, I'm going to say relative to Earth, though. All right, then describe V. Velocity of the cell phone relative to Earth, though. And then describe V prime. That would be the velocity of the cell phone relative to the balloon. It's all about establishing two different frames of reference, two different potential observers who can see this cell phone fall. Now, after 4 seconds, what's going to be the speed of the cell phone relative to Earth? So we want to write down what's given. So one thing that's given is the initial speed of the balloon. All right, so let's say we did a little motion graph of it. And it's a position versus time graph. Then what we would see is the balloon, let's say, starts on the ground at time 0. And as time goes on, the balloon is getting farther and farther off the time axis because it's moving in the positive y direction, right? So it's steadily rising here with 2.98 meters per second, and that could be the slope. And it would also be called VI. And I'll just call it VIY relative to the vertical dimension. So it's going to be 2.98 meters per second. That's going to be the slope of the thing. Now, when the cell phone is released, it doesn't just suddenly head toward ground. Instead, it's going to carry with it that momentum that it had from the balloon's motion. And it will now enter into a parabolic free fall path. All right, so here, the initial slope would match what the slope was for the rising of the balloon. But it's a piecewise type of thing, where there's a definite change in the motion at that point of release. So this is a point of release. We want to write down what the VIY is. 2.98 meters per second. We could write down what the acceleration due to gravity will be in free fall. It'll be negative though. All right, now what kind of formula could we use to perhaps figure out the speed of a thing? Well, we could use this idea. Initial plus change equals final. Or, in other words, final equals change plus initial. But what type of physics quantity are we talking about, though? How about velocity? Vy final equals the change plus the initial. But how do we represent the change of a velocity? There's a formula for acceleration, which is a change in velocity with time. So we just want to rearrange it to find that the change in velocity will be the acceleration times the time, and apply that to the y dimension. So that's actually what we're going to put in here. All right, we assume that the cell phone is moving relative to a person who's watching it from ground. So if a person is standing here on ground, stationary, they believe that cell phone is traveling upward when it's released. And so when you do the calculations, you do put in the 2.98. So you do this. So the final velocity after 4 seconds will be, looks like negative 36.2 meters per second. All right, in these calculations, I don't really necessarily have to put the J hat in. It's like a choice that you make whether you want to show it or not. This is just a one-dimensional problem, so it's not really necessary. We can let the sign of the answer tell us the direction. And this is a negative, so that means that the cell phone is falling down relative to the person who's watching it. Maybe it's like right here. Well, it asks for the speed. The speed is the magnitude of the velocity, so speed would be 36.2 meters per second. But it is moving downward. Now let's find the displacement of the cell phone as measured by the person who's on Earth. For that, we would use the familiar formula delta y equals 1/2 ay t squared plus viyt. And we would just do everything as normal, as if it wasn't like a relativity problem, you know? So delta y equals 1/2 negative 9.8 times 4 squared plus 2.98 times 4. All right, I'm getting negative 66.5 meters. All right, so from here, the point of release, to here, the point, after 4 seconds has passed, I'll call this 0 as far as my labeling goes. And this can be 4. 0 is the point of release. 4 is the point we're interested in, so 66.5 meters dropped. It fell 66.5 meters. Now, the tricky question, the one that involves relativity. Find the displacement of the cell phone as measured in the balloon's reference frame. All right, so the thing about the balloon is it's moving, like let's say there's the basket, and it's just going to keep rising even after the cell phone is dropped. Okay. And so the cell phone will take that parabolic path But what's being asked is the displacement from the balloon's perspective, which would not be called delta y, but delta y prime. Let's do a formula for delta y prime then. You'd have to use 1/2 ay prime times t squared plus viy prime times t. And remember, it's not meaning derivative of those things. It's meaning relative to the balloon rather than relative to ground. One thing about acceleration is that if you're in any constant velocity reference frame, so like let's say you've got here your frame S, which is stationary on Earth relative to the person on Earth. Then you could have another frame, S prime, and let's say that S prime is the balloon's frame. Both of these frames are going to see the same acceleration for objects. So we're going to find that A prime is equal to A. It's going to be negative 9.8 for both. And Einstein addressed this when he talked about his general theory of relativity. He said, like, if you were in a box, like an elevator, and you were falling, like all the objects in that elevator would have the same acceleration, but you wouldn't know that you're falling if you were in it. Let's plug in the things that we need. All right, so we'll have negative 9.8, 4 seconds of time, but what is our VIY? VIY prime would be the motion of the cell phone relative to the balloon operator, for example. Like as the cell phone is rising with the balloon operator, what is that cell phone's velocity relative to the balloon operator is the idea. Yeah, it would be 0 because the cell phone and the operator are traveling together. Does that make sense? So like the cell phone's not moving up or down relative to that operator. Like he could even have it in his pocket, the cell phone, or in his hand, and that cell phone would never get away from him until he dropped it. And once he dropped it, it would feel the acceleration of being pulled down. Let's see what the delta y then will be. Negative 78.4 meters. It is larger. It's more than what it was relative to Earth. And to explain why it's larger, check this out. This would be a drawing of the distance between the cell phone and the balloon as the balloon rises. So the distance would be 78.4 there. But the person believes, let's say this is the point of dropping. See, the person who's observing from ground thinks that that was the delta y. But the person who is in the balloon thinks that the delta y is much more. So whereas this would be 66.5 meters from the initial launch point to where it ended up, the person in the balloon would think it was farther away from himself.